Welcome. So we are discussing about the topic process synchronization. Under process synchronization, we are discussing about the solution to the problem critical section. So last class we have discussed that any solution to the problem of critical section should have three characteristics. That is, the solution should ensure that the solution should ensure mutual exclusion. That if one process in the critical section, if one process is in its critical section, then no other process should be allowed to enter its critical section. And the second characteristic is progress. That is, no process should be infinitely waiting to enter the critical section. And the third characteristics is bounded wait. That is, if a process enters critical section right now, then it should wait until the other process enters the critical section, and only when all other process enters the critical section and comes out, then only this process should be allowed to enter the critical section. So in today's session, we'll be discussing one of the basic solution, and also it's one of the original solution which is proposed for critical section problem. And this solution is called as Peterson's solution. This solution assumes just two processes. Okay, so we assume there are only two processes which are concurrent process, and they share the common variable. They have a common shared variable, and if this process uh, uh, should and if this process should be synchronized properly to ensure that the shared variable is consistent, then then we can follow this Peterson's algorithm. Okay, so the Peterson solution, it contains two shared variables. So what are the shared variables here? uh, I mean, the proposed solution, it uses two shared variables. Okay, apart from the shared variable that the actual processes access, apart from that, the solution itself uses two shared variables. One is called as turn, and the other one is flag, which is of Boolean type. Turn is of type integer. So the turn contains the value like it is whose turn. Okay, so in the previous case also we have discussed an algorithm with a variable turn. So there we have only one variable turn. Here we have two variables. One is turn, the other one is flag. So if we assume the two processes as I and j, if we consider the two processes as I and j, then turn can hold either the value of I or j. If turn is equal to I, then it means that it is ith turn. That is, it is ith turn to enter the critical section. If turn is equal to j, then it means that it is the turn of the jth process to enter the critical section. Similarly, we have another variable flag of 2, which is a Boolean variable. Flag of, so basically it is an array. So there is two locations in this array. So you can consider this as flag of 0 and flag of 1. So we can say it is flag of the two locations in the arrays, or flag of 0 and flag of 1. Flag of 0 will be equal to true. Flag of 0 will be equal to true if the ith process, or flag of 0 will be equal to true if the ith process want to enter the critical section right now. Similarly, flag of 1 will be true if the jth process want to enter the critical section at this particular time. Okay, so here we use the solution, the proposed solution in Peterson's algorithm. They use two shared variables. So these are turn and flag. So these variables are turned shared between both the process I and j. Now let us go through the algorithm. This is the algorithm. So what it says in the sense, basically it is an infinite loop, and in the beginning it says, so this is the algorithm for I. So we have two processes pi and pj which should be synchronized. So this is the algorithm for pi. Okay, so pi, what it does in the sense, it makes flag of I is equal to true. It means that this particular process want to enter the critical section. It is making flag of I as true, which means the ith process want to enter the critical section. Okay. But at the same time, it is making turn equal to j. Okay. At the same time, it is making turn equal to j. It means that if if j want to enter, let it enter. So that is what this statement. So that it is making turn as j, and then it is checking, it is executing this while loop flag of j while flag of j. So flag of I is true, that we know because ith process has made it true. But what is flag of j, we don't know. Okay, if flag of j is true and turn equal to j, and turn is j, turn is j, that we know. So this is true, this is true. But flag of j is true or false, that currently we don't know. If it is true, if it is true, then it means that jth process also want to enter the critical section. If flag of j is also true, then it means that jth process also want to enter the critical section. So if j is also true, then this while loop will return true, then this while loop will return true. So if it is returned true, then so you can see there is a semicolon here, which means there is no statement inside the while loop, but it keeps on checks this condition as long as this condition returns true. So if jth process also want to enter the critical section, then this will be true. This is already true. So both true and true, it will result in true. Then it will keep on wait. Then the ith process will keep on wait, and it will keep on checking these two things. What is flag of j and what is turn equal to j. Turn is always j, but it keeps on checking flag of j. Okay, so it keeps on wait until jth process becomes false. Okay, so as long as jth process is true, it will be waiting. So if jth process is true, then what does it mean? If jth process, if flag of j is true, then what does it mean? If flag of j is true, what does it mean? It means that jth process want to enter the critical section, and it will be entering the critical section obviously, and it will execute the critical section. And while coming out of the critical section, what jth process will do in the sense, while coming out of the critical section, it will make flag of j equal to false. When it comes out of the critical section, it will make flag of j as false. Okay, it will make flag of j as false. So the moment it comes out of the critical section, flag of j will be false. So if flag of j is false, then automatically this condition, it will become false and true, and it will be written false. So then the control will get into the critical section for the ith process. Okay, now the ith process will execute its critical section, and then the ith process, after completing the critical section, the ith process will set flag of I is equal to false. That is, no more I need critical section. Okay, now if j want, then it can execute its critical section. Okay, so this is the entry section, this is the actual critical section, and this is the exit section. So this is the algorithm for process I. Similarly, you can write the algorithm for process j. Okay, so what will be the algorithm for process j? Instead of I, here you have to put j. Flag of j is equal to true. Okay, and turn is equal to I. Here you have to assume that jth process will assume that it is ith turn. While flag of while flag of I while flag of I and turn equal to I. As long as it is flag of I is true and turn is equal to I, it will wait, because let I completes, further it will wait. Okay, and then it will, if this condition fails, then it will enter the critical section. When it is coming out, it will make flag of j is equal to false. Okay, so this is a very simple algorithm which is proposed by Peterson to solve the critical section problem, and it is a quite successful algorithm. Okay, so let us discuss this algorithm with an example. Okay, so let us assume there are two processes. One is Alice and the other one is Bob. Okay, and there is a Alice and Bob, both of them, they were using a shared variable, and that shared variable is x. Alice and Bob were using a shared variable, and the name of the shared variable is x. Okay. So Alice wants to perform an operation on x, and that operation is called as frob. Actually, frob does not mean anything, it is just a name. Okay. Alice want to perform some operation on x, and that is called as frob. And Bob want to perform an operation on the same shared variable x, and that is called as borf. So Alice want to frob it and Bob want to borf it. Okay. Now, as this is a shared variable, these two processes, if it executes concurrently, then x will become inconsistent. So to ensure that x is not getting inconsistent, okay, so we can use Peterson's algorithm here. Okay, so how it works, let us see. So this is the x is the shared variable which is commonly shared between Alice and Bob. Okay, so there are two variables, A wants and B wants. Okay, so it is similar to in the algorithm whatever we have discussed, flag of I and flag of j. Flag of I is equal to true means I want to enter the critical section. Flag of j is equal to true means j wants to enter the critical section. Similarly, here we are using, instead of that array, we are using different variable. A wants and B wants. Initially, both are false. That is, A don't want to enter the critical section and B also don't want to enter the. Then we are using an enumerated data type which contains A and B, and we are creating a variable for this enumerated data type turn. So turn can take two values. Turn can take any one of the two values. It is either it can take the value A or it can take the value B. Okay. So either it can take the value A or it can take the value B. If turn is equal to A, it means it is A's turn. If turn is equal to B, it means it is B's turn. Okay. Similarly, if A wants equal to true, then it means that A want to enter the critical section. If B wants equal to true, means it means B wants to enter the critical section. Now this is the Alice code for process synchronization, and this is the Bob's code for process synchronization to ensure data consistency. Okay, so what Alice is doing, so A represents Alice. Here A represents Alice and B represents Bob. So what Alice is doing is, Alice want to for frob X. Okay, so Alice say makes A wants as true. A wants equal to true. Because Alice want to perform an operation on X and that operation is frob. So he makes A wants equal to true. And at the same time, Alice is making turn equal to B. That is, if B also want to perform an operation on X, let B do that. So that Alice is making turn equal to B. Okay. Then Alice is checking this for while loop, which is ends with the semicolon, which means there is no other statement inside the while loop. And as long as this condition is true, it will it will it will it will loop around. Okay, spin loop. Okay, so so it checks while B wants and turn equal to B. Okay, while B wants and turn equal to B. So turn is B, that we know. Alice is setting turn as B, so we know turn is B. But we don't know whether B wants is true or not. If Bob also want to perform an operation at the same time, then B wants will be true. If both of these variable are true, then this will become a spin loop or spin lock, and Alice will be keep on waiting. Okay, so it means that during that time, Bob is in the critical section. So Bob will execute his critical section, but once the critical section is over, so this is the critical section, Bob is performing borf. Once the critical section is over, Bob will make B wants as false. Bob will make B wants as false. Okay, so if at time t naught B wants is true, if at time t naught B wants is true, and at time t4 say it becomes false, then till time t4 Alice will be checking, keep on checking what is B wants and what is turn. Turn is B, that is not going to change, but B wants will, at time t4 it will change. It will change to false. There is no more B wants to enter the critical section. Okay, then this while loop fails, because false and true it will become false. So now nobody is in the critical section. Now Bob is not in the critical section and this while loop fails. So Alice enters the critical section and Alice will perform his operation, which is frog. So Alice performs his operation and then he sets A wants as false because his critical section is over. So now he makes A wants as false. No more he wants. So the same thing for Bob also. So if Bob want to perform critical section operation, then Bob sets B wants as true because B represents Bob. So Bob want to perform a critical section task. And at the same time, Bob is making turn equal to A. Okay, Bob is making turn equal to A. That is, if allies also want to do, let allies, if allies also want to access the critical section, let allies access. That is what, so that only it is making turn equal to A. Then it checks while A wants and turn equal to A. Turn is A, that we know in Bob's side, but A wants is true or not, that we don't know. If A wants is also true, then Bob will wait until A completes the critical section. Once A completes the critical section, A will make A wants as false. So then this while loop will fail, and then Bob will enter the critical section and Bob will perform borf of X on that particular shared variable. And while coming out, Bob will make B wants as false. Okay. So this is how this algorithm works. So in the last lecture, we discussed one solution for critical section problem, but there we used only one variable turn. We have not used this A ones and B ones. And that algorithm, it also solved the problem of critical section by ensuring mutual exclusion, but it fails with respect to progress. But it fails with respect to progress because after process one, it forces process two to enter the critical section, and again it forces process 1 to enter the critical section. That is, it should always follow ij that order. Okay, so that is the drawback with that algorithm. So to overcome that particular drawback, in Peterson's algorithm, two variables are introduced, not just one variable, two variables. One is turn, the other one is the particular process wants to enter or not. Okay, so this algorithm, it ensures all the three conditions for the critical section solution. Okay, so as we know, any solution for critical section should satisfy three conditions. First is it should ensure that mutual exclusion is satisfied. So here mutual exclusion is satisfied. If allies is in the critical section, then Bob will not enter the critical section. Similarly, if Bob is in the critical section, then allies will not enter the critical section. Okay. If allies is in the critical section, then A wants will be true. So Bob will not enter. Similarly, if Bob is in the critical section, then B wants will be true. So allies will not enter the critical section. So mutual exclusion is satisfied. Okay. And okay, and progress is also satisfied. So that problem will not happen. Like if allies if ally, it is not that first allies should enter, then Bob should enter, then allies, then Bob. That problem will not come. Assume that assume that currently allies want to enter the critical section and Bob don't want to enter the critical section. If Bob don't want to enter the critical section, then B wants will be false. Then obviously allies will enter the critical section, and again allies will set his A wants as false and he will come out. Okay, but again say immediately allies want to enter the critical section, but Bob don't want. So then allies will come and do this A wants equal to true and turn equal to B, but still B wants is false. So allies will continuously can access the critical section if B don't want to access the critical section. Okay, are you getting? So if Bob wants to access the critical section, then first allies will access, then Bob, and then allies, and then Bob. Okay. By that it ensures progress. Similarly, it also ensures bounded wait. So bounded wait in the sense, if both allies and Bob wants to enter the critical section, then either one of them will get, either A will get or B will get. If allies gets first, then immediately once allies comes out, then the next turn, even immediately next, if allies wants to go, that cannot happen because Bob is waiting. So first it will go. So once allies comes out, the turn will be given to Bob, and then allies, and then Bob. Even if both of them want to access continuously, it will follow this order: allies Bob, allies Bob, allies Bob. Okay. But if both of them don't want to follow continuously, if only one of them want to access, then also they can access. Okay. So if only one want to keep on access, that is possible. So it satisfies progress. But if both of them want to access continuously, then if allies access first, then next the turn will be Bob and next allies. So by that it ensures bounded wait. So all the three conditions actually the Peterson's algorithm satisfies. So it is one of the simple solution for critical section problem. Okay. But the drawback with this algorithm is it is used in older days. In modern computers, it is not used. The reason is it is basically designed for two processes. It assumes that there are only two processes which are competing to enter the critical section. But in today's scenario, that is not the case. There may be more than uh, two processes. So in that case, it may satisfy mutual exclusion. It satisfies mutual exclusion, but it cannot guarantee about progress and bounded weight. Okay. So that's it about Peterson's solution. So let us stop here for this session. Thank you.